Alright, so the requirements of this project, basically we're controlling 9 RGB LEDs, RGB meaning red, green, blue LEDs, using 4 8-bit serial input parallel output shift registers, and the Nexus 1 FPGA board to output signals to each of the red, green, or blue pins on the RGBs. And of course using minimal microcontroller lines. And the key behind this project is pulse width modulation to get the full spectrum of colors. So that's basically the key behind our software. And once we have that, we can create more dynamic and creative patterns.
So if you guys know what an RGB LED is, essentially it is, you guys are all familiar with a regular LED right here, red LED. Well, an RGB LED has the same, has 3 LEDs combined in it. So as you can see here, there is actually 3 different pins, each composed of a different LED and a common ground. So what happens is, let's say this is the ground, if you apply a voltage here, red turns on. If you apply a voltage here, green turns on, and blue. What this is, if you apply voltage in both places, you can get red and green both turned on, which you'll see as a different color than red and green, whenever that combines to, I think it's yellow. Okay, and pulse modulation before we brief interview. Actually, what's on this slide?
So basically with pulse width modulation, we can combine the red, green, and blue in using different duty cycles for each of the colors to create a full spectrum of colors. The really simple colors you can create are the secondary colors, and that it just basically involves having one of the R, G, or Bs completely off. So for example, if you have R and B, you can create magenta, G and B, cyan, green, and red, yellow. And so then the rest is just basically getting all the colors in between.
So to do that though, so essentially before is on this LED here, you have two voltages applied here, you get one solid color. Red and green are completely on. But if we could turn red kind of on, or a little dimmer, then we can get a full spectrum of this red and green color. So you can get light yellow, dark yellow, cyan, deep cyans. And so this is where pulse width modulation comes into play. What you do is you keep one pin high, so let's say you keep the red pin high for 90% of the time. Such as, let's say, duty cycle. Let's say this is an 80% duty cycle here. Well, if red's on for this long, you'll see it pretty bright. If red's only on for, let's say, 20% of the time, it's dimmer. If you do this quick enough, your eye can't tell the difference. So as long as your duty cycle period is sufficiently small enough, you can get this red LED to be really dim or really bright.
So this combination here would be a really unique color of R, G, and B. So like what Dan said, this would be the dimmest, this would be the brightest, and this color would be in between.
Sure, so this pulse width modulation represents one complete color. These are red, green, and blue. Red would be on half the time, green would be on 80% of the time, blue would be on 20% of the time. So by modifying these in all different combinations, you get an almost endless amount of colors you can use. We got hardware architecture here, pretty basic. So we're using the microwave processor, pretty similar. We're using the timer to generate our pulse signals. Let me explain the shift register system here. So essentially before, if you have one LED, you would need let's see, my controller with 3 pins. Your microcontroller could control this line, and this line. But you need 3 lines from that controller. But since we're using 9 RGB LEDs, we would need 9 times 3, 27 control lines from the microcontroller. Not something that's really feasible on most microcontroller systems. So what you can utilize is a shift register. So this is our Nexus board here. It's feeding data in, and a shift register essentially we feed it the 27 values. If you want a shift register on or off. So it loads a 0, 1, it boots the 0, 1 all the way down here. And then finally, our slow clock, our output enable, turns these on. So we have a fast clock that loads data in, it goes really quick, loads 0 and 1 all the way through, and when we're completely loaded, we say, okay, enable the output, and slam this all onto like the LEDs essentially. Okay. So essentially how this program works is that Kind of complex. I don't know if you guys really want to go into the full details of the code there. Okay, so essentially the design came as this. The first test is we need to make the Nexus board create a 27 pulse to drive the shift register. A shift register shifts everything over on a clock pulse. So you get a pulse, shifter moves things over. Another pulse, go over. So there's 27 times, so all the data comes into the shift registers. And then we figured out a way to pulse width modulate each of those pins, essentially. And then from there, it's just creating patterns and whatnot. It was kind of a truncated, I guess, description of how the system's working. Any general questions on that idea? Yeah, please.
What frequency are you running the LEDs at?
As fast as we can, actually. So I just kept going. The timer's running, I think, at 10. I love the timer's value of 10. And once it finishes, yeah, because I mean, I'm driving 27. We need a fast clock of 27 of these things in, and then do a pulse width modulation. So essentially, to pulse width modulate, what you do is, let's say an overall period of 1 second, and we have 64 different increments in our pulse width modulation. That means we need to load this with one set of values, 1/64th of that time period. So you gotta go crazy quick, change it crazy quick. You gotta do this all for pulse modulation. So it's, I mean, the export is maxed out right now, how quick we can go. That being said, I still think we could probably drive maybe 4 or 5 more LEDs on there, on the data line.
So your actual period then of changing all the LEDs then is one second?
No, the LEDs change very quickly. So the question is, they are being written
For one pattern to the next.
One pattern to the next changes very quickly. Because, so let's say we want to turn, let's say all these are on, and let's say we're just controlling the red of this LED here. So if we want this to slowly increase color, this is going to start, this will be on 1/64th of a period. This will go for a little while. And then we'll make this on 5/64th of a period. Then we'll go on 20/64th of a period. And then 4/64th of a period. So it's going pretty quickly.
So your overall display rate then, what is your frequency?
I don't know the exact number, but it's pretty high up there.
Well, we'll take a look at it.
Okay. All right. Well, maybe this will be better. I'll show you guys the actual what it's doing. Is these the lights right here?